continues to explode. Mobile wireless networks must expand greatly their capabilities, capacities, data rate, and reliability. Resources are scarce and they need to be optimally utilized to obtain the maximum benefits so that we can facilitate the rising demand. Researchers and service providers are working on various avenues to meet the challenging demand of the customer, which is growing rapidly as mentioned. I, Mohammad Osama Zahid, is here to bring one of the new and very interesting topic which has great potential to meet the stringent requirements of the data rate, capacity, and reliability, presenting Beamspace multiplexing derived from beamforming and spatial multiplexing. Topic today I'm going to cover is physical layer technologies in 2G and 3G, MIMO technology, MIMO classification, beamspace multiplexing, simulations, and salient. In the last, beamspace capacity and comparison. Physical layer technologies in 2G and 3G. In the last 20 years, cellular system technology evolved mostly revolve around time and frequency domain. Physical layer technologies improved in different areas like time frequency multiplexing, multiplexes waveforms, modulation schemes, and coding schemes. MIMO technology. It's a technique for sending and receiving more than one data signal simultaneously over the same radio channel by exploiting multipath propagation. Under the umbrella of MIMO, MIMO is classified into three further substreams, that is spatial multiplexing, beamforming, and transmission diversity. We will explain all these concepts very briefly. First is the spatial multiplexing. It's MIMO technology where multiple antennas at both the transmitter and receivers are used to carry multiple data streams at the same time within the same frequency band. And objectives over here is that any one of these can be employed but not simultaneously. You can either increase throughput or reliability. Then we have beamforming, a MIMO technology in which wireless signal is directed towards specific receiving device through changing the phases of antenna elements. And objectives over here are is to increase signal quality through SNR and less interference. The third one is the transmission diversity. In such a system, the receiver is provided with multiple copies of the same information coded differently, signals which are transmitted over multiple communication channels. And objectives over here is to enhance the reliability through orthogonal encoding. Spatial multiplexing. When objective is to increase the throughput, the message is broken into multiple compartments. Like over here, we have a message, we have broken this message into different compartments like S1, S2, S3, S4, S5. And all of them are transmitted simultaneously at their respective antennas. So this statement said that each compartment is routed to independent antenna element where all those compartments are sent simultaneously, resulting into increased throughput and data rate. For instance, if we have a transmitter which is equipped with NT, that is 10 antennas, and receiver with NR antennas, and R we can consider it as 5. The maximum spatial multiplexing is of the order is mathematically expressed with this mathematical equation. So if we put NT over here 10 and R with 5, the minimum we get is 5. So 5 streams can be transmitted in parallel, ideally leading to 5 time increase in spectral efficiency theoretically. Then we have a beamforming. Beamforming used with phased array antenna systems to focus the wireless signal in a chosen direction, normally towards a specific receiving device. This results in an improved signal at the user equipment and also less interference between the signals of the individual user equipment. Over here we have three illustrations. In the first illustration we have only one antenna element, and you see this is the radiation pattern we obtain. But if we have two antenna elements together and we are feeding a signal to both of them with different phases, we obtain relatively a narrower beam. And if we increase more antennas in an array, we get much narrower beam width, and it will point towards a certain direction. So if we change the phases at the input of the antenna array elements, we can steer and we can direct the beam at different directions so that we can accommodate different users or user. So main control, the main controlling element is the phase shifter, which is present at the input of the each antenna element. So we can control the beam by changing different phases at the input. We can also use the beam forming in another configuration, which we can create different subsets. Each subsets is controlled with different phase shifters and different signal input. So different users can be accommodated also this configuration as well. Now, since we have covered both the concepts, that is the spatial multiplexing and beamforming, we are now in a better position to focus on this new concept, which is Beamspace multiplexing, and it is defined as spatial multiplexing based on beamform enabled multiple activated data pipes to enhance capacity, throughput, and SNR without extra power consumption. In beam-space multiplexing, we have array gain, beam steering, multiplexing gain, interference reduction gain. Very briefly, I'll explain. Firstly, the array gain. An array gain from multi-antenna user can prolong battery life, extend range, and provide higher throughput. Increase in mean SNR due to coherent combining, and for that requires channel knowledge of transmitter and receiver. And it also depends on the number of transmitter and receiver antennas. Then beam steering, that is the beam forming. It's all about changing the direction of the main lobe of a radiation pattern. So in radio and radar systems, beam steering may be accomplished by switching the antenna elements or by changing the relative phases of the RF signal driving those elements. Then the multiplexing gain. Multiple stream transmissions can provide higher data rates, and all of them are transmit independent data signals from individual antennas. Receiver can extract different streams under uncorrelated fading channel conditions, and a linear increase in capacity for no additional power or bandwidth cost is also obtained. Interference reduction gain. Transmit or receive interference reduction combining can increase the signal to interference plus noise ratio and also improve link reliability and robustness. This is simulation of antenna array radiation pattern by increasing the number of antenna elements. So over here we have an antenna array in which each element is of omnidirectional type. Operating frequency is 1 gigahertz. We are changing 1 to 10 antenna elements, and the antenna element spacing is 250 millimeters. This simulation shows the effect on radiation pattern when an array of omnidirectional antennas is configured operating at 1 gigahertz, and with this settings, as I have already mentioned, antenna array beam gets narrower. If you see over here, that is approaches to pencil beam when elements are increased, leading to array gain.